trigonometry students, my name is Jami Emigh, and this video starts our discussion on Chapter 8, title Complex Numbers, Polar Equations, and Parametric Equations. Let's start by talking about the natural numbers. You can see here 1, 2, 3, 4, 5. It's a very natural way of counting, if you will. After that was the introduction or the formal proof of the whole numbers, which would be all the natural numbers plus 0, followed by integers, and that would be the natural numbers plus the whole numbers plus the negatives. So this whole group right here is called the integers. When we are able to put those values into the form of a fraction of an integer over an integer, we are now working with rational numbers. There's a set of irrational numbers as well. These cannot be put into the form of an integer over an integer. And this entire subgroup right here is called the real numbers, a plus bi, such that b equals 0. So really it has no bi portion. And I'll talk to you about what I is. Let's go over here and talk about the pure imaginary numbers. These are of the form a plus bi as well, but b does not equal 0. So we can't cross that out. We have to have some imaginary part. So 3i, negative I. These are the imaginary parts. We call them pure imaginary numbers because they don't have a real part. So no a. So what we're starting to break down, if you're picking up on it, is here the real part is a, and here the imaginary part is the bi. Non-real complex numbers, a plus bi, have both parts. So we have a real part, so 7, plus an imaginary part, 2i. Here's another example. 5 is the real part, minus I times radical 3 is the imaginary part, and one more. Negative 1/2 is the real part, plus 2/3 of I is the imaginary part. These are non-real complex numbers. These have a real part, lowercase a, and an imaginary part, lowercase b. The pure imaginary numbers have no real part. That's why we crossed out the lowercase a earlier. And numbers that can be put into rectangular form, a plus bi, is a represents the real part and b represents the imaginary part. The imaginary unit, lowercase I, is equivalent to the square root of -1. Therefore, if we squared both sides of this equation, we would get I squared equals -1. So taking it from here to here, just square both sides, and we get a value for I squared, at being -1. The definition of the square root of -a, if a is greater than 0, so the negative is there, but then this is positive, so we have a negative underneath the radical sign, then the square root of -a is equivalent to I times the square root of positive a. Know how to get from here to here, okay? This is important, being able to get from the square root of -a being equivalent to, take the imaginary portion out, and we have radical a here. And this is a product, okay? They're multiplied together. Let's look at some examples. Write each of the following as the product of a real number and I, using the definition that we just went over, where the square root of -a is equal to I times the square root of a. All right, first one, radical -70. So we are being asked to write this value right here as the product of a real number and I. So this right here would become separating out the -1 from the positive 70, resulting in I, which we write out front, and radical 70. This is the real number, and this is I, and this is a product. So we've done exactly what they asked. Write each of the following as the product of a real number and I. Try this one. Go ahead and pause the video and try it now. Welcome back. If you came up with 4i, you got it right. Here are my steps that I took. Your work may look slightly different than mine, but as long as you're making all legal moves with no mistakes, you should get to 4i. I like to write mine as separating the -1 and the 16 through multiplication, then taking this right here, turning it into its equivalent I, and leaving the radical 16. Taking the root of 16 is 4. Notice here, this one we left as radical 70, and that is because 70 is not a perfect square. So you may have taken this to a decimal. You can try to work with this here, but leaving it in an exact form is radical 70, whereas radical 16, leaving it in exact form, simplifies to 4. All right, let's take a look at when we have a radical, -7 times a radical with another negative underneath. What we can do here is take the negative portion, it's represented with the I out front now on both of these. Then we take the product. So I times I gives us I squared. Radical 7 times radical 7 is radical 49. I squared is -1. This is one that I said we want to remember this one. Whenever we see I squared, we want to change it to -1. And that was from way up here, okay? Make sure you are remembering this one. I squared is -1. And the square root of 49, well, 49 is a perfect square, so keeping the exact value, we can simplify it to 7, no problem. And then that becomes -7. So a lot of steps here, basically to show what the development of this, but you will probably get comfortable with just going radical -7 times radical -7 is -7. Just like radical 3 times radical 3 is radical 9, which becomes 3. Operations of complex numbers. So let's talk now about adding, subtracting, and multiplying two complex numbers together. All right, here's a complex number, a plus bi. Let's add it to another complex number, c plus di. So we're working with this one right now, the operation. If you are adding two complex numbers, you add the real parts, that's the a and the c, plus sign. You add the coefficients on the imaginary part, so I, so you add b and d, and it will result in I. This might look like a lot, but it's really the same as combining like terms. If this had been, let's say, 5 plus 10x plus 6 plus 11x, you find the terms that have x's on them, combine those. You find the terms that do not have x's, combine those. Combining like terms. You guys have done that a lot. Same deal with subtraction. If you have a complex number and you are finding the difference between that and another complex number, think combine like terms. Now be careful, we do have this negative, so you do want to make sure that you distribute that first, just like you would have done if there were no imaginary parts. Distributing that negative, and then combining like terms would be adding the real parts, so a minus c, and adding the coefficients on the imaginary parts, so b minus d. Third operation of complex numbers, multiplication. So there's an invisible multiplication sign right here. You can go ahead and distribute this. Some people call it FOIL when it's a binomial times a binomial. You can do that. You can do a times c, and this would give us a times di. This would give us cbi. Whoops. This here would give us bdi squared, and you can continue working with that, or you can use its equivalent form, which for this one, I like to turn this into a blank template and then plug in my A, B, C, and D to see what I get. Let's do an example of each. perform the operation. Here we have a complex number plus another complex number. Pause the video and tell me what you would get. Welcome back. If you went with thought process combining like terms, getting you to 1 plus 2i, nice work, you did it correctly. That is because the 3 minus 2, those are the real parts, combine them to get 1. Negative 4i plus 6i, those are the imaginary parts. Combining like terms, if you will, or adding their coefficients gets us 2 i's. Pause the video and try to subtract two complex numbers. Welcome back. If you distributed that -1, we have something that results like this here. And then you think combine like terms. So we're going to combine the real parts and the imaginary parts, giving us -10 plus 10i. Nice job, you got it right. Let's try a multiplication of two complex numbers. So I'm going to suggest that you set up a blank template. It looks like a lot right here. It came directly from this. Anywhere that I saw an A, a C, a B, or a D, I turned it into a blank like that here. So now I'm going to take A, which is 1, that gets plugged in here and here. B, which is 2, that gets this spot and this spot. C is 3, that gets this spot and this spot. And finally, D is -4, so that gets this spot and this spot. Then we just have to be careful with our arithmetic, and we're done. Here's what that looks like with all of those values plugged in. Simplifying gets us this whole part right here, simplifies to 11, and this whole part right here simplifies to 2. All right, I want you to pause the video and try these 3 examples now. Welcome back, grade your own. If you got -76 plus 8i for the first one, you got it right. If you got 10 minus i for the second one, you got it right. And if you got 5 plus 4i for the third one, you got that one right as well. If you didn't get those right, then check my work, try to find your error, okay? What I want to move on to now is looking at the representation of this. Each of these can be represented by a vector, so that's why this is called vector representation. The first vector right here, 1 plus 3i, we would go, you start at the origin, okay? You go over to 1, and then you would go up 3 units. It's like this is the real part of the complex number on this axis, the 1, and then up, this is like the imaginary part. So we go over 1, up 3. That being our final destination, then we just draw the vector. Here's our second complex number, 4 plus bi. In vector representation, we would start at the origin, go over 4, up 1. That's the point right there. Draw the vector. And now the addition of these two, we got the answer of 5 plus 4i. So what does that look like using vector representation? It's actually taking this path right here, start at the origin, go over to 5, go up to 4. That is the final destination, and this vector represents the sum of this vector and this vector. That may sound a little bit confusing, but think about it as walking, okay? You start right here. Let's say you walk this distance. So now you're standing right here. You turn and you walk this path. Well, this path right here, if you can see from this parallelogram, This path right here is the 4 plus I. So adding them together, think about it as walking those two paths. So if you started here, you walked to here, and then you walked to here, and you would end up right here. Well, the addition of those two vectors would just be taking the shorter path, starting here from the origin and walking directly to the point right there. And that vector right there in red can be represented by our answer, 5 plus 4i. So great job working with the numbers, but this is what it would look like in vector representation, which we're going to talk about in more detail here. The complex plane uses rectangular form and trigonometric or polar form to represent complex numbers. Okay, so here is what looks like the rectangular coordinate system with addition of those labels that we added in that last example. We have the real axis and we have the imaginary axis. Each complex number, a plus bi, determines a unique position vector with initial point 0, 0, okay, so we start at the origin, and the terminal point, so where we end up, at a comma b. So for this one right here, we start at the origin, we end right here. The coordinate of that terminal point is a comma b. So in this example, it's 2, -3. Let's put some notes on this. That point right there is 2, so a comma -3, that's b. The length of this vector right here, we can find, it's the square root of 13. We're going to find that using the Pythagorean theorem. But before we do that, rectangular form would just be taking the 2 on the real axis, minus sign because we're going down on the imaginary axis, -3. We tack on our I, and 2 minus 3i. That is the vector that you see here in blue, represented in rectangular form. There's another way to represent it called trigonometric or polar form. And you want to be flexible between those two. Some books call it trigonometric, some will call it polar, some books call it both. They mean the same thing, trigonometric and polar form. I like the name trigonometric form because, as you can see, it's got trig operations in it, so trigonometric form. I also like the name polar form because polar, it is found by traveling around a circular path rather than rectangular form where you go side to side, up or down. Polar form, you would go like this. Radical 13, that's the radius or the length of this vector. So you would go out, radical 13, and then you would go in a circle 304 degrees. It looks something like this. Let me change colors. It would look something like this, going out a distance of square root of 13, that being our initial side, and then rotating that till it hits the terminal side, and that would be a 304, if we're talking degrees, degree angle. So it is the same vector. This vector is the representation, but it can be represented as 2 plus 3i, or as radical 13 times cosine of 304 degrees plus I sine of 304 degrees. All right, so that is a breakdown of this title of this slide, the complex plane using rectangular form and trigonometric or polar form to represent a complex number. Let's go with this one here. Let me erase all on my pen. All right, let's use this one as an example now. We have this vector. It has gone over -4, and we're not going up at all. So it's like walking from here to here. Okay, the rectangular form of this would be The real axis, we traveled -4, so we write -4 plus how much we traveled on the y-axis, or the imaginary axis. And for this one, we didn't move up or down. That's why the y-coordinate is 0. So the imaginary part is 0i. So that would reduce to just -4. So the rectangular form for this vector would be -4. For this complex number is just -4. The polar form would be the distance traveled, so from the origin to here. That's why you see a +4 right there. It's the magnitude of the vector if you have studied that at all. And then it's the angle in which the initial side, so let's show it here. If we started here initially, traveling to 4, and then rotate till we hit the terminal side, that is where the 180 degrees come from. Two representations of the same complex number. This one is called rectangular form. This one is called trigonometric or polar form. Okay, complex numbers of rectangular form, x plus yi, can also be written in trigonometric or polar form, r times cosine theta plus I sine of theta. So this right here is everything we just talked about in the last slide, but in their general form. Now notice with the polar form, it's a lot of writing. You have to write the r, so the magnitude of the vector, the radius of the circle, the distance traveled from the origin, if you will, open parentheses, cosine of theta plus I sine of theta. But we know that this language of mathematics, we try to abbreviate everything we possibly can. So this right here can be abbreviated down to r, so that's holding on to that, but the cosine, the I, and the sine, just writing it as CIS. And then theta, it has to be the same angle, so no need to write it twice, we would just write it once. So this is an abbreviated trigonometric or polar form. Let's look at this complex number, x plus yi. Here we have vector representation of that. Its magnitude is lowercase r, or the radius of the circle, should we construct it, is lowercase r. Theta, you can see represented here from the initial side to the terminal side. We have dropped a vertical line so that we can construct a right triangle so that we can apply the Pythagorean theorem. I said a few slides back that we were going to find r using the Pythagorean theorem, and here it is now. R is the length of the vector. So to find r, we would use the Pythagorean theorem. R squared, or the hypotenuse squared, is equal to one of the legs squared plus the other leg squared. Isolating r would be r equals the square root of x squared plus y squared. And we only have to talk about the positive or the principal root because we are using it to represent the length of the vector. Theta is the angle of the vector. Theta can be found using tangent of theta is equivalent to y over x. X cannot be 0 because that would be we would be undefined there. What are y and x? They are right here. X is r cosine theta. Y is r sine theta. So those would get plugged in. So we would set it up as, here we go. We would change the x into r cosine theta plus sine, r sine theta for y, I. We would factor the r out. So this should look familiar to you. That's the general trigonometric or polar form. And then we would abbreviate it into r CIS theta. Example. Let's write this complex number, negative radical 3 plus I, in trigonometric form, and we're going to do so using radians. All right, converting from rectangular to trigonometric form. Here is the strategy that you're going to want to use. Step 1, sketch the graph in the complex plane. All right, so set up your x and y. Negative radical 3 plus 1. I'm going to highlight the 1 there for emphasis. So you would start at the origin. You would go over negative radical 3, up 1. From that point right there, you can sketch the vector, drop a vertical line, and find the length of this vector using the Pythagorean theorem, which would be the square root of x squared plus y squared. X is negative radical 3, substituting that in. Y is 1, substituting that in, simplifying, and it turns out that this vector right here is 2 units long. This might look familiar to you from special triangles. This one has a special name. It's called the 30, 60, 90, where the shortest side is 1, the hypotenuse is double that, and the other leg is a length of radical 3. We have a negative here because we're showing this traveling in this direction. Nonetheless, there's r equals 2. Step 3, we need to find theta. So we're going to find theta using tangent of theta being equal to y over x. Y we know is 1. X we know is negative radical 3. So we're going to do tangent of theta of 1 over negative radical 3. Just rationalizing the denominator, that's all that happened from here to here. Just rationalizing the denominator. We're in quadrant 2. That's noteworthy because that's going to help us with our sign, and that would lead us to theta. So tangent would have to be of theta, 5 pi over 6, to get us negative radical 3 over 3. And you can find that using the tables. So pull your tables out, find the tangent column and the row negative radical 3 over 3. You're going to find 2 of them, but then you'll narrow it down to 5 pi over 6 because we're in quadrant 2. Okay, we have found r. We have found theta. That's all we need. We write r, which is 2, cis, and then theta, which is 5 pi over 6. And that's step 4, writing it in trigonometric form. Here it is in the non-abbreviated form, and here it is in the abbreviated. Please note that both forms, trigonometric form in general, it is dependent on r and theta. That's why we did one step to find r, an additional step was to find theta. Once you find r and theta, you can rewrite your complex number from rectangular form into trigonometric or polar form. All right, let's do this example. Let's write the complex number negative 3i in trigonometric form. Solution trigonometric form is r times cosine theta plus I sine theta, and therefore we need r and theta, just like the last example. Negative 3i is our complex number. Writing negative 3i out so that it shows a and b, or x and y, if you will, would look like this. Okay, this is important. Knowing that negative 3i can be written as 0 minus 3i. That's necessary so that we know we can plot the point x equals 0, y equals negative 3 on our graph. So the point 0, negative 3 is right here. Vector representation right there. Polar, we need this as our theta right there. And just remind yourself, we only need r and theta. I bet just looking at this right now, most of you can come up with r and theta. If you said r equals 3, nice work, because counting, that would be 1, 2, 3. And for theta, if you said 270 degrees, you got that right as well. And that is because terminal side lands on the bottom of the y-axis right here. That is a 270 degree rotation from the initial side. So we take the 3 and the 270. Abbreviated form is just 3 CIS 270 degrees. Please pause the video and try this example now. Welcome back. Let's see how you did. If you came up with, let's get all the way to the final answer. Final answer is 1 minus I radical 3. If you came up with this right here, you got it right. Nice job. Let's break it down now. Solution, rectangular form, which we're being requested to put this number into, is x plus yi. That means that we need x and we need y. Well, we know x is equivalent to r cosine theta. We know r is right here, it's 2, and we know theta is right here, it's 300. So we can find x. It's just 2 cosine 300. 2 cosine of 300 degrees is 2 times 1/2, which is 1. So we found x. This is x. Done. The other thing we need for rectangular form is y. We know that y is equivalent to r sine theta. So again, we've got 2 for r, sine and theta equals 300. That is 2 times negative radical 3 over 2, which is negative radical 3. We have found y. And that's all we need. We need x, we need y, and we can write this in rectangular form. X is 1 minus I radical 3. That's y and the imaginary I. Graphically, that would look like we need to go over to 1. Let's put that as 1. And then down to negative radical 3. Let's say it's right about here. So starting at the origin, vector representation would get us to that point right there, 1 negative radical 3. If you want to show rectangular or polar representation, that would be theta equals 300 degrees. That would be r equals 2. And complex number in rectangular form is 1 plus I radical 3. The product theorem. Here we have a complex number in trigonometric or polar form times another complex number in trigonometric or polar form. If you're being asked to multiply two of these together, the process has been proven for us and it's quite simple. So we just have to embrace the proof, okay? Take the length of your first, the length of the second, and multiply them together. So we get r sub 1 times r sub 2. Then open our brackets, cosine of, and we add the angles together. So we've got theta 1 and theta 2. So these ones get added together right here, theta 1 plus theta 2, plus I sine and the same, theta 1 plus theta 2. Close brackets. I kind of like the abbreviated portion better because it really shows that right from the start, if you're being asked to multiply two complex numbers from trigonometric or polar form, you need to take the r for each, multiply them, CIS, and the theta from each, and add them. Let's try one. We have 3 cosine of 45 degrees plus I sine of 45 degrees, and we're being asked to multiply that with 2 cosine of 135 degrees plus I sine 135 degrees. Okay, remember what we're going to do. We're going to multiply the 3 and the 2, and we're going to add the 45 and the 135. Looks like this. 3 times 2, that's from here, and 45 plus 135. That's here. Oh, I think I have a typo. This is supposed to be 45 plus 135 degrees, which I think is going to equal 180. Must have just made this too quickly. That gives us 3 times 2, which is 6, and 45 plus 35, which is 180. We write it here the second time, or we can write it in its abbreviated form, which is 6 CIS 180 degrees. But leaving it in this form here actually becomes more beneficial at this point. So leaving it here, we keep the 6. Now we find the value of cosine of 180 degrees, which is -1. Then we have a plus sign. Then we have I. Then we find the value of sine of 180 degrees, which is 0. So here we simplify to get -6 and plus 0i. That simplifies slightly more, just to -6. Okay, let's check out the quotient theorem. And like the product theorem, I like to look at the abbreviated form first. Here are two complex numbers in polar form. Their quotient, see how the abbreviated form makes it a little more easy to see. We take the two r's, so r sub 1 and r sub 2, we find their quotient, and then we take the two angles, theta sub 1 and theta sub 2, and we find their difference this time. So quotient and difference. Contrary to the product theorem, for that one we did product and sum. Okay, so product theorem, think product of the r's, sum of the angles. Quotient theorem, think quotient of the r's, difference of the angles. Let's see. Here we're being asked to find the quotient of these two complex numbers. So we take the 10 and the 5. Their quotient is 10 over 5, which that's going to reduce to 2. And then we find the difference of the angles. So right here, that would be -60 degrees minus 150 degrees. And that would give us 2 and -210 degrees. In abbreviated form, we have 2 CIS, -210 degrees, abbreviated polar form. If we took it out of the abbreviated, we have it in its extended form here, and we want to do this because we can find the value of cosine of -210 degrees and the value for sine of -210 degrees, simplifying this expression to 2 times negative radical 3 over 2 plus I times 1/2, which simplifies to negative radical 3 plus I. And that is how you find the quotient of two complex numbers. There's a French mathematician, Abraham du Mauvoir, I believe it's pronounced, alive in 1667 to 1754, and his theorem is that if r cosine theta plus I sine theta is a complex number and n is a real number, okay, and needs to be real, then you can take your complex number to the power of n. Lots of steps in between, but we're just embracing the proof, which sends us to, you take the r, raise that to the nth power, take the angles, multiply those by the nth power. So you can see it here on the other side of the equal sign. R has been risen to the nth power, and the angle has been multiplied by n right here as well. Let's try it. Find, here's our complex number, and we're being asked to find its 8th power, okay, raising it to the 8th power. We take the 2, so the r, we raise that to the 8th power, and we take the angles, so the 120 degrees, and we take their 8th multiple, so multiplying them by 8. That becomes 256 cosine of 960 plus I sine 960. We can find the least positive coterminal angle, so instead of working with 960, subtracting out multiples of 360 gives us the least positive coterminal angle of 240. Then we can use our table tables with the sine, cosine, and trig function values on them, to substitute the value, which is negative 1/2, and again, substitute the value from the table, which is negative radical 3 over 2. Simplifying that becomes negative 128 minus 128 radical 3i. The nth root theorem says take a complex number. It has n many distinct nth roots. To find those roots, we would take the nth root of r and multiply that by cosine of a new angle plus I sine a new angle. We're going to call that new angle alpha, and alpha can be found by taking the original angle listed, theta, divided by n, but then we need to add on 2 pi over n times k. K always starts at 0, and then it's going to climb up until we get to n. So let's look at this through an example. Find the square roots of 4i. Square roots means n equals 2, okay? Let's take our 4i and extend it in a polar form like this here. And now we're going to take r, which is 4, and remember, right here, this is what we're going to do. We're going to take our 4 and take the square root of it. Then we're going to take our theta and we're going to turn it into alpha. So we're going to do this part right here now. So we take our nth root of r, which is the square root of 4 in this case, which is equal to 2. Now we're going to take our theta, which is pi over 2. We're going to use k equals 0 and 1 because that will get us to 2 many roots. See, we're trying to build up to 2. Okay, every time you guys start with k equals 0 and then build up until you have the number of roots that we're being, or whatever n equals, asked to find. Okay, so for that, alpha is going to be equal to, we take the original theta, which is pi over 2, divide it by n, which is 2, add on to that 2 pi, and we're starting with k equals 0, and this is over n. If you simplify this right here, you get pi over 4. So that is one of our values for alpha. Now we need to do it again. We need to change the k from 0, increase it by a full integer. So now we're looking at if k equals 1, and if k equals 1 this time, that simplifies to 5 pi over 4. That's another value for alpha. So the square roots of 4i are 2 CIS pi over 4, came from this one, and 2 CIS 5 pi over 4. So it turns out that the square roots of 4i are 2 CIS pi over 4 and 2 CIS 5 pi over 4. Example, explore the fourth roots of 16 CIS 120. All right, I want you to pause the video and try that now. Welcome back, grade your own. If you wrote down that n equals 4, nice job, r equals 16, and theta equals 120 degrees, good start. From there, we take the fourth root of r, which is 2. Next, we take theta divided by n plus 360 divided by n, starting with k equals 0. That gets us our alpha equals 30 degrees. Then we go again. We change k into 1. That gives us 120 degrees. We're going to go again because we need to get all the way to 4 of these. So we have 1, 2, we need 2 more. So if you plugged in k equals 2 next, good job. That gets us to 210 degrees. And finally, plugging in k equals 3. It's every time, you guys, start with k equals 0 and make sure you do as many as needed to get to n many. That is 300 degrees. Okay, so we have found the 4 roots. They are 2 CIS 30 right here, 2 CIS 120 right here, 2 CIS 210 right here, and 2 CIS 300 degrees right here. And this is a really nice visual of what we actually did. Sometimes it's easy to just get caught up in the number crunching, but here we see that the graphs of these roots lie on a circle with its center at the origin and has a radius of 2. That's what we found here. And the roots are equally spaced about the circle. So if you notice, they are each 90 degrees apart for this particular example, giving us 30, 120, 210, and 300. All right, that finishes our discussion for chapter 8. So please do the chapter 8 homework now. And my name is Jami Emigh. Thank you for being here. I will see you next time.